Hi everyone, Mr. Ford here. Today on your asynchronous day, we're going to walk through the third kind of variation of vectors in our vectors packet. So far, just as review, we've taken two vectors that were either in the x or the y direction, added them together to get the resultant, or we've taken one singular vector that was not in the x or y and broke it down into its x or y components. So hopefully over the homework you looked at the answer key and everything makes sense. If it doesn't, please send me a Schoology message. I'll have limited availability on Wednesday, but may have a free moment or two to get back to you or send you like a video or audio recording. So here we go. This is going to be on page 3 of our vectors packet. If you've been through pre-calc or calc, this is going to be kind of a review. Some things are going to be a little different. Some tips and tricks that you've learned in calc you might not be able to do in physics. If you're in pre-calc now, no worries. We're going to go through the unit pretty much that nobody has any experience with it. So the steps are here. Again, take these equations with kind of a grain of salt, meaning they're only going to work if you stick to a specific method of solving these problems. I always say kind of ignore them and just use the trig functions as you know it. Draw a triangle, you have an angle or sides, and use SOHCAHTOA or Pythagorean theorem as you have already known. So here we have Jeff walks 2 meters at 60 degrees and then 4 meters at 120. Do not draw the following. This is what sometimes in pre-calc or calc, or I'm not sure the math class, that you'd learn this in. So you would draw the 2 meters at 60, and then the 120 at 4. That kind of looks like 4. So the issue here is if we were to think of, what we've been doing, tip to tail method, and then draw like our starting and our ending point, this is not a right triangle. Even if we kind of force it to be like, oh, that looks like a right triangle, it's not actually a right triangle. At some points in those geometry or pre-calc or calc classes, you use probably law of sines to go through in each little section to figure out angles and then get the overall result. That will work in this case to get the answer, but in a physics problem, we're going to be looking to break things up into x and y components and get those x and y totals, and being able to use just those x components and those x totals in one equation and the y in potentially another equation. So this is technically a little mini math lesson, but we're using it in terms of what we're going to see in the future with physics. Okay, so what we're actually going to do here is, again, different color pens or pencils or highlighters definitely can help out when sketching these ray diagrams or vector diagrams, or what in the future is going to become force diagrams, just so we can separate like vectors, components, angles, some of our work, and it keeps things a little bit organized. So we here have Jeff walking at 2 meters, 60 degrees, roughly 60 degrees. And then what we're going to do is separate them and work on them individually. So here we have two vectors. So in the steps, we need to take one at a time, just like we did before, and break it down into their x and y components. Just by habit, I like to always sketch in my coordinate system, just get a frame of reference of where things are, like my 0, my 90, my 180, my 270. And I have my x component, my y component, and this problem's pretty easy because it gives us, relative to 0, everything in these problems, that initial angle is going to be relative to 0, meaning the right, or positive x direction. So that's my 60. Sketch in my other one, making to note that I'm drawing to the left. That red arrow I just drew to the left, so that's going to be a negative number. Forgot to draw in my coordinate system here. So my 120 degrees that I'm provided is relative to 0, so it's this big angle here. But since I'm going to use Pythagorean theorem and trig functions, I probably want to look at my triangle just as it were in a geometry class. So to straight left is 180 minus my 120. That gives me my inside angle as 60, just like the other ones, just by coincidence. So how I'm set up, I have an angle and I have a side, so I can use sine and cosine. I'm going to start off with sine. So sine 60, that's equal to opposite over hypotenuse. So my opposite side is my delta y. My hypotenuse is my 2 meters. I'll eventually plug that into a calculator, making sure I am in degree mode, not radian mode. That's a big thing in physics, because in your math classes at this level in high school, you're probably in radians in math, but then in physics, you're going to be going back into degree mode because it's not a calc-based course. So then to get my delta x, cosine 60 is delta x over 2 meters. And very similarly, with our other vector, we're going to do sine 60 just because it's the same angle. Delta y is over my 4 meters. Kind of mislabeled. Sometimes I get a little too happy when I keep things consistent. There we go. Everything's red, everything's green. So then cosine 60 Now that I've done this, I just want to have a little discussion that you may have chosen to draw the triangles that are on top of those vectors. That's all well and good, right? This triangle here, or this one here. Just note if you have drawn them, again, I am a proponent of whatever you see to sketch and kind of follow that through. But my solutions always will, if I can, have one of my components being drawn on the x-axis. So if you, for some reason, like the y-axis, by all means, go ahead that way. Just know that there may be a little bit of extra figuring out of the work if there comes up a wrong answer. So when I plug that in my calculator, I'm just going to label these as best I can. Let's expand a little bit. And for my sine 60 here, my delta y over 2 meters, is going to be 1.7 and 1 meter. I just want to confirm something real quick because I was looking at my work from earlier and may have noticed something, a flip-flop thing, so just want to be clear. Okay, so that's why I did that. Yep, we're all good. And then for our 4 meters at 120, we go through, plug in our trig functions, and we get 3.5 meters. And this is the tricky part. technically for my delta x in my 4-meter one, I don't need a negative sign because if I label this diagram, I already have an arrow going to the left. But what tends to happen if we don't take the time to write that -2 in an equation or in just an answer kind of slot without putting an angle or a north, south, east, or west to show the direction, we need that positive or negative. So just by tradition, I think I've mentioned this before, my junior year of high school physics teacher, whatever he did kind of ingrained it into my brain that you don't need to put it. So traditionally, I know I say traditionally so many times, which something kind of interesting. Earlier, I was saying, all right, you're good to go in some breakout rooms at the last class of the day, and students thought that meant that it was good to go and leave the class. So I got to watch my kind of phrasing. So this is how I kind of tend to write. So I got my 2 meters displacement in my x direction, and the arrow shows to the left. But when we start to write that in for adding components, if you know that you're going to tend to not see that arrow or it's a different color, take the time to write that negative in there. So for my delta x total, I have my 1 meter plus, and we're totaling, so we're getting a sum because we're adding, and that negative just means that measurement was in the opposite direction. And then my y's. So you can see the importance of being organized, writing all your units, how you solve problems, or how you're doing your calculations in these kind of problems, because we're only about halfway through this question. These are very meticulous, and one little, miscalculation or writing the wrong number, delta y, delta x, sine or cosine, 60 or 30 degrees can kind of throw things off. So that's fine, mistakes will happen, and that's the importance of putting down all your work, showing all your diagrams, your work, so that if I see there's just a negative missing here or a flip-flop of sine or cosine or 30 or 60 in this case, minimal point loss, it was just a simple mistake. Okay, so we broke those two components, those two vectors down into their x and y components. We added them together, so we have their totals. Now the second half starts. So this is like what we first did. Now we have two component vectors. We're again going to put them together to find one total resultant. I know it's a lot. So we have our -1 meter, so to the left. Feel free to put that there. We'll call that 5.2 meters. And rounding is up to you. So just know in solutions, whether it's in this video or other solutions posted, if you plug everything in all one shot in a calculator and you get a different answer than I do, it just is likely due to rounding differences. So we definitely have our right angle because they're x and y. And we're going to go blue here. Here's my final answer as a resultant. So I have two sides, no angle other than 90. So what do I do to get my answer? Hopefully we're saying we're going to go ask Pythagoras. So use Pythagorean theorem, a squared plus b squared equals c squared. And that's really close to that other angle, which makes sense because we have one component's 1, other one's 5.2, so it's going to be closer to that 5.2. Definitely bigger than both of them individually, but smaller than their sum. Okay, so we got our magnitude, our size of our resultant. And I apologize for the confusion of like what this is and this is. We'll talk about that. I'm really flexible with, as long as you show your work in a detailed manner, how the end result is, I'm kind of flexible in figuring things out. So now we need to figure out which way we're going. So if we're going to put our coordinate system in, say like right here, because that's where our resultant started, it's good to note that a lot of teachers, professors, textbooks will say your theta, right, this number here, or this symbol here, is always going to be relative to the right being 0. But just the way that I was taught, and I think you guys, if you have an unknown angle, you tend to put that in the triangle as theta. That's the symbol of an angle, right? So right now we're going to search for or calculate for that angle right inside that triangle. So I have all my sides. I kind of have freedom to pick whatever I want. SOHCAHTOA, sine, cosine, or tangent. I'm just going to pick tangent since that's what I didn't calculate, at least in the beginning part of this. So opposite over adjacent. 5.2 is my opposite side. Yeah, it is negative. For this course, you don't really need to go through and look at the negative, what that means. It will still spit out in your calculator the same angle. It just is kind of relative to your unit circle and which way you go. So that will give us 79 degrees. So I'm not sure if Mr. Mackman thought we were going to go like this route and say, okay, 79 degrees. And then down here, find that real angle that's relative to 0. Oh, let's pick another color. Say here in orange. So great, we have a diagram, and in the future, I think I've mentioned before, we're going to always have pictures or diagrams and say like 79 degrees relative to, our negative x-axis. Or we'll have a picture and we have our 79 degrees, or we have our theta literally written in there as we see in front of us. So if that's a little confusing, no worries. But if we are going to figure out relative to that 0 being right, we need to see that we have wrong button here. Our negative, meaning our 180 degrees, is going straight left. And we have a portion of that is 79. So to figure out to that blue arrow, we simply take 180 minus 79. And that would give us 101 degrees as our resultant direction. We could write this also as 5.3 meters at 101 degrees, but this just kind of separates it, which is fine. And then the equilibrium is just the same magnitude, just the opposite direction. So to get the opposite direction, if we are less than 180, we just add 180 degrees. So that's 281. If we are bigger than 180 degrees, then we subtract it. So what you're going to do today during class is kind of fish out some of the packet problems with Bob, Lisa, John, and then we're going to skip a few, and you're going to do number 6 on page 6. The answers are on Schoology in the homework folder. The answers are actually within the Mackman packet if you want to do some extra. But I'm going to walk through, no pun intended, Bob walking 3 meters at 320 degrees and then 5 at 135. If you're good to go and you're confident, you can kind of stop the video here and then go on your own and just check the Schoology solutions. If not, you can refer back to this. So I think this might be a little bit different just because of the angle. Sometimes people get tripped up with the unit circle and having this big 320 degree angle and then figuring out small angles within a right triangle. And it's kind of funny how math works. Myself, I struggled did pretty well in Algebra 1. Algebra 2 struggled, was one of the students who got like a lot of C's, had to come in before school for extra help. Still, that didn't really help, never kind of clicked. And then was in an honors class in Algebra 2, went down to geometry in like an academic level. It was called college prep level. And I got like 100 for the year. It was too easy because algebra and geometry is a little different. Went back up into honors in calc, or it was trig. We didn't have pre-calc and calc, and kind of went up and down throughout high school and college. So math is a little funny that way. Certain topics click, some don't. So hopefully applying them to realistic scenarios this year will help. All right, so we got Bob going at 320. That's about, say there. I'm going to put in my coordinate system just for reference. So that 320 was this huge circle. So if you couldn't envision where that was, sometimes it's helpful to put that in there. Now I add in my X and Y components. I need to know what my interior angle is for this triangle. So if I know the full circle is 360, and then I have kind of outside my triangle is 320, the inside angle there is going to be 40 to make my full circle. So then my other vector component is 5 meters at 135, which is about, say that. Draw my components. Again, I'm going left. So that's going to be a kind of little hint that there's going to be negatives involved, just like my down in my one that I drew to the left. So this is my 135. If to the left is 180, my remaining that I don't have inside my triangle is going to be 45. And I celebrate and say yay, because if one side's 45, the other side's 45, I only need to do one trig function because it's going to be an equilateral triangle where both x and y components are the same size. So that's why I say yay. So just like I did before, I tend to start with sine. I don't know why. So sine is opposite over hypotenuse. So delta y over my hypotenuse of 3 meters. To get that side, to get my x, cosine, adjacent, adjacent is my delta x side over my hypotenuse. Just kind of showing my work first. For the right picture here, my 5 meters at 135, it really doesn't matter what I pick. You can almost not go wrong here, because whatever one side is, the other side's going to be. So I plug that into my calculator, again being in degree mode, and I'll get the following measurements. Making sure if I'm going down, I put that negative reminder in. Or if you really want, you can call up and to the right negative if you like. Forgot to label these. I'm just labeling these in the beginning just because there is some kind of, as I label them wrong. some confusion with saying displacement, and we focused on delta x in the beginning, but now that we're looking in 2 dimensions, delta x and delta y are still displacements, but just in a specific direction. And this is 3.5 meters. Going to the left, so make sure, put that in there. And then kind of filling in my blank lines here. And I do this on purpose. I am totaling things, so I'm writing a sum. So I definitely want to have a plus sign. And then negative is just to emphasize a direction. And we take a breath because we're halfway done. And now we have to sketch those 2 components into one resultant. Can you go green? So we have our positive delta y, so it's up. And I kind of drew this backwards. And our negative 1.2 delta x. And the resultant hypotenuse, as we see here. So we have right angle, we have 2 sides, no angles. What can we do now? Just like last time, go ask Mr. Pythagoras. A squared plus b squared equals c squared. Plugging that all into a calculator, we would get 2 meters. And that kind of satisfies this part. We have all 3 sides. We can use whatever trig function we like to find our angles. I'm going to define this is what I'm trying to find. And just note, I'm going to eventually figure out what this huge angle is relative to 0 being on the right. I'm going to pick tangent. So opposite over adjacent. So my 1.6 over my technically negative 1.2, but that doesn't really matter for us right now. Plug that in, we get this interior angle of 53 degrees. So what I define as theta, that's 53. But thinking of actual direction of my resultant relative to 0 degrees being right, I take 180 minus my 53 to get that missing angle. That's 127. That's less than 180, so I would add 180 to get the opposite direction, and that's 307. So hopefully that made sense with those 2 walkthroughs. Feel free to go back into the homework solutions to look at them again, statically maybe. The next thing is going to be to go through and figure out what happens with Lisa and John as they walk. So you're going to find their resultants and then skip all the way down to 6. 6 is very tedious. I wouldn't say it's difficult. It's just going to be 3 vectors. So you're going to have to break down 3 different vectors and have 3 different delta x's and 3 different delta y's, add them together, just as we did with Jeff and Bob previously. So if you're still watching the video, after you've done those steps in the packet, you're going to move forward to complete a Schoology quiz for next class. It's 19 questions. It's not all as difficult as this. It might be simple. A simple question like, off the top of my head, which one of these is a vector quantity? Distance, speed, or velocity? So hopefully you could answer those. Some of them are more difficult and will require some more work and thought, like number 6 here. But that'll give me a good idea going into next class, your level of understanding. There are 2 attempts. If during either this video or this work today you have any questions, or during your Schoology quiz, be sure to send me a Schoology message and I can reach back out to you. And I will see you guys on Friday.